We are starting a series of videos for our Statistics OER course Unit 6 on sampling distributions. This video will concentrate on introducing the sampling distribution of the sample means. If you want to reference our textbooks in the Intro Stats by OpenStax, we are in section 7.1, the central limit theorem for the sample means. And in Lumen, we are in module 7, titled the central limit theorem, and we are in the introduction to the central limit theorem for the sample means. In this particular video, we will first introduce the distribution of the sample means. And that is, we will do a few experiments and some statistical investigations to discuss what this is. So the first thing we want to do is we want to remind ourselves what we discussed in Unit 2. In Unit 2, when we did the descriptive statistics and we learned how to find the mean of a sample or the mean of a population, we also discussed about the sampling distribution. And the sampling distribution is a distribution of some particular statistic from the population, not the distribution of the data values. And we will focus in this first section of Unit 6 in the mean of a sample. So to refresh our memory, the mean of the sample can be calculated in two different ways. One is we can add all the values up and divide by the total. So in this particular example, we had 30 students and 5 of them said that they saw 0 movies. And then 15 said that they saw 1 movie. So I will add 1 plus 1 plus 1 15 times. And then 6 said that they saw 2 movies. And 3 said that they saw 3 movies, and 1 said that they saw 4 movies. So the way to find the mean would be to add all of those and divide by 30. And that is 0 times 5. That will give us this first 0. 1 times 15, which is the this 15. 2 times 6, that's the 12. 3 times 3, that's the 9. And 4 times 1. So we can do that. We can say 0 times 5, and then 1 times 15, and then 2 times 6, which is a shortcut of adding those this many times, and then plus 3 times 3, and then plus 4 times 1. I'm going to write it here because I don't have space. And then we divide by 30. So that's one option. The answer would be 1.3 movies. There is another option, and that other option is to actually take every single one of them and divide it by 30. So create 5 separate fractions, each one divided by 30. And when we do that, then what happens is that every one of our data values is multiplied by its relative frequency. 5 out of 30, 15 out of 30, 6 out of 30, 3 out of 30, and 1 out of 30. So when this happens, there is another way of calculating the mean of the sample, and that is to multiply every data value with the relative frequency or the proportion of values that we end up getting in our sample, and that also will equal 1.3 movies. So going back to the sampling and the sample mean concept, let's assume that we have a very small population of 20 students who were asked how many times they went skiing last winter, and let's assume that each student said a different number from 1 to 20. So this was kind of a uniform distribution. It is not a continuous variable, but if it's a discrete variable, but if we were to kind of approximate it, we have the variable of number of times they went skiing last winter, and this variable is uniform with a lowest value of 1 and a highest value of 20. Remember that when we use this notation, we assume that x is continuous, but for now we will use it to see the correlation between a continuous variable versus the discrete variable. Now, if we use the formula, the mean is lowest plus highest divided by 2, 10.5 times, going skiing. And the standard deviation, the theoretical one for the continuous variable, was the square root of 20 minus 1 squared divided by 12. That comes out to be approximately 5.5. I want to find the exact values because these are 20 discrete values and I can do that. So I have created here an Excel file that has the values from 1 to 20. X is the variable of number of times they went skiing. The mean can be found by using the average function of the array from 1 to 20. And it also happens to be 10.5. And the actual standard deviation of a population here for this particular array will be approximately 5.8. So the actual one came out to be approximately 5.8, and these are all measured in the same units as the variable, which is number of times they went skiing. So now that we know the actual mean and the theoretical standard deviation and the actual standard deviation, we can now proceed to take samples of this population as if we had a larger population and we couldn't access it all. So now we have to do some sampling and draw some inferences for the population. So we will use a random number generator. In fact, we will use a lot of other methods, but for now we want to draw simple random samples of size 5. And I'm going to use first a random number generator. So I'm going to go here. I did a search here for a random number generator. And then a lot of options showed up and I selected this one, the calculator soup. It asks you for the range of values. I want to go from 1 to 20. And then it asks you how many numbers you want to generate, and I want 5. Do you want repetition? No. Do not sort. Generate one set, and I'm going to hit calculate. And it generated a set 13, 6, 1, 4, and 9. 13, 6, 1, 4, and 9. And let's have it generate one more set for us. So let's click calculate again. 12, 5, 18, 7, and 8. I'm going to put it here. 12, 5, 18, 7, and 8. And let's calculate the mean and the standard deviation. Remember, this is a sample. So even though I will use the average function, there is only one function for the average. For the standard deviation, I will use the standard deviation.s for sample. And I have a mean of 6.6 and a standard deviation of 4.6. You can already see that the mean of 6.6 is actually very small compared to the theoretical mean, the mean of 10.5 of the population. So let's try the next group of random values. This had a mean of 10, which is much closer to the actual population mean, but it's not exactly 10.5. I'm going to ask Excel to generate random numbers, so I can use RANDARRAY, and it asks me how many rows. I say 5 rows, comma, how many columns. I want only one column. what's the minimum and the maximum, 1, 20. And the next part if whether you want an integer or a decimal. I have to say true for integer. I want integers. So it generated this 1, 13, 13, 17, and 2. Let me copy it here because it tends to, just run the random array every time. So these were my original. And you see here that 13 appeared again twice. It repeated. So that's what we will leave it as is for now. Hopefully the next time we will run it, it won't do that. The mean this time was 9.2. In my class, I would, in person, we would just have students pair up and generate really quickly about 10 means or so. Let's do it one more time. Equals RANDARRAY. And I want 5 rows, 1 column, 1 is the min, 20 is the max, and true for integers only. So I'm going to get this one. 8, 1, 9, 11, and 5. 8, 1, 9, 11, and 5. You see, every time you do something in Excel, the RANDARRAY regenerates 5 random numbers. So let's copy the mean and the standard deviation calculations so we don't have to redo them. And I got a mean of 6.8. All right. We will try some more later. So as you've noticed, if no matter how many times I would try it, I would never get 10.5 times as the mean for my sample. So we have 2 questions. We have one question is, why do we get different means? And the other question is, why do we not get the mean of the population? So why were our means different from other means? The answer is we had different samples. This is called sample variability. So between samples from the same population, your samples are different, and therefore you get different answers. And then the other thing is, why do we get, even in the same, why if we have 2 different samples don't we get the same data values? And the answer is that people answered different answers. There was data variability. So the answers we get to our questions are not all the same. And that's a great thing. Like, that's the reason why we have statistics. If we were all the same height, or if we were all going with the speed limit or the same, if we were all automated, then there will be no variability. But because we are not automated, there is variability in nature. Now, another thing that we want to observe is that the lowest value of x is 1 and the highest is 20, but the lowest value for the mean is not 1. Because for you to get the lowest value for the mean, you have to have randomly selected the lowest 5 values in your set, and the mean of those would be 3. So that will be the lowest mean you could ever get. And if you wanted to, if by accident you had randomly selected the 5 highest value in this population, then the mean of that sample would be 18. So we didn't get the lowest mean possible and we didn't get the highest mean possible, but the value of the mean, the lowest, the minimum and the maximum for the mean itself is not equal to the minimum and the maximum for the data value. And the reason is that your sample consists of different data values, since we have data variability in the population, and therefore you don't get your sample to always have the lowest, all of the observational units in your sample to be corresponding to the lowest data value X. That's extremely unlikely. If I allowed repetition to get 5 ones, or if I allowed repetition to get 5 20s. So always keep in mind that when you have a sample, which is your method of doing some observation or some study of the population, your sample is different from any other sample, and also your sample contains some of the data of the population, but not all of the data of the population. So the next question that we want to know is, if this was repeated multiple times, what would these means look like? So when I ask my whole class to do the same experiment repetitively, and I get different values for the means, what do these means look like? Why did I get 2 values close to 6.8 and a 10 and a 9.2? I don't know what else would have happened, but for now, all of these values happened to be smaller than 10.5, which is the actual mean. So I didn't get anything above 10.5 for some reason. So hopefully if you have enough, you will get more than that. So that's our question. The question is, all of these means, what do they look like? And statistically, this is called, what is the distribution of the sample means? So another way of collecting samples actually is to go to ArtofStat and do that. So I'm going to go to ArtofStat in the web apps, and I have here sampling distributions and the central limit theorem. The first one is the distribution of the sample proportion, which we will see later in Unit 6 of this class. And the other two are sampling distributions for the sample mean of continuous populations and sampling distributions of the sample mean of discrete populations. And since the example we did today was discrete, let's try to do that. So this is an example of Amazon star ratings, and the ratings are discrete from 1 to 5, and they appear with these probabilities listed here. And you will see here the population distribution with probabilities with relative frequencies. And we can pick sample sizes of, let's say, size 20. This is the default. And I can draw a sample. Here is 1. How many samples do you want? I want just 1. And let's draw a sample and see what happens. So it drew a sample of size 20 that contained 4 1s, 1 3, a bunch of 4s, and 6 5s. And then it sketched here the frequency bar graph. So I had 4 1s, no 2s, 0 2s, 1 3, about 9, it looks like 4, 9 4s, and 6 5s. And the average of those happened to be 3.65. The mean of the population is 3.4, and it is shown here as a semicircle sitting always on the same location. So the first sample mean was 3.65. If I draw another sample, it will draw a different set of 1, 2, 3, 4, 5 ratings, and it will calculate another mean, and this mean happened to be 3.55, which now is placed closer to the actual mean of the population. Let's draw another sample. That will be our third sample. Here is the new mean. It is 3.42. Let's do another sample. The mean was 3.31. And now to speed up the process, so instead of just selecting one sample at a time, let's select 100 samples. and it will give us the information for the last one. Okay, that's what happened. After it has done 100 more samples on top of the 4 that we drew first. This is what the means looked like. There were several samples that had actually kind of the same value of the mean, accurate to 2 decimal places. Let's do another 100. Let's do another 100. Let's do another 100. Let's do 1,000. All right, so hold on. Let's do another 100. There we go. Let's do another 100. There we go. Let's do another 100. Let's do 1,000 now. So as you can see, the value of x, the lowest value is 1, and the highest value is 5, but we haven't gotten any means that far to the right or that far to the left. So our means tend to gather around the mean of the population that was 3.4. And here we did get a very low mean. We got a 2. It looks like even less than 2.5. This particular mean, oh, it is right here. It is 2.3. I see it up on this title. So we got a 2.3. And that was kind of an unusual mean. It came all the way to the bottom. But if you pay attention here, the distribution of the means tends to look like a bell-shaped symmetric distribution. The mean of those means was 3.39, and 3.39 is very, very close to the actual mean of the population of 3.4. Let's try something else. So let's try the word length in a speech by Judge Sotomayor. So the judge gave a speech, and the words ranked from 1 letter words to 16 letter words with these particular probabilities. This is the distribution of the words. The most popular ones were 2, 3, and 4 letter words. And let's draw samples of size 20. And let's draw one again and see what that looks like. So that sample had these 20 words. The highest was 8 letters. And the frequencies are shown here. Again, most of them were 2, 3, and 4. Since they are very descriptive of the population, it looks like. The mean length of words in the judge's speech, the mu of the population, is 4.68. And this particular sample ended up with a mean of 3.9. And a standard deviation of 2.02 instead of 2.61. All right, let's draw one more sample. There we go. This sample did a little better. It had a mean of 4.9, a standard deviation of 2.1. So it's a little closer to 4.68. Let's draw another one. Okay, we are even closer to the actual mean. We have a sample with 4.65 mean. This is the word length. We have a new sample of 4.4 to expedite this process. Let's draw 100 samples. Okay, so the means of the 100 samples are placed here. And you see our last sample had 5.45, which is a little farther away from the mean upwards, but it's still within the sample means that we have collected before. Let's do another 100. Let's do another 100. Let's do another 100 samples. Let's make it 1,000. And again, you see that the distribution of all of those sample means tends to generate values very close to the actual mean or around the actual mean. And we don't get averages that are equal to 1 or to 8, to 16, whatever was the highest. We are actually really far away from those possible values. None of our samples ever gave us any of those values. The highest we went, the lowest we got was like 2.8, and the highest we got was less than 7. So we stayed in this area. What is this again? This blue graph here in the bottom is the distribution of the values of the mean length of words from samples of size 20 coming out of the population. So one option that we have here is to build a custom distribution. And to build a custom distribution of 20 values, we want to add here our values 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And remember that they were all equally likely to occur. Each one of them was 0.05. And I'm going to copy this. Let me see if I can do that. All right, 0.05. So everything was equally likely to occur. And if you paid attention, this is our population. And I'm going to do sample of size 5. Let me reset. Okay, here we are. I'm going to draw my first sample of size 5. It drew a 3, a 13, a 15, a 19, and a 20. The mean was 10.5, correct? The standard deviation was 5.77. That's what we found it to be when we did our calculation in Excel. This particular sample had a mean of 14 and a standard deviation of 6.78. So let's draw another sample. That was one time going skiing, 9, 10, 14, and 20 going skiing. This mean came out to be 10.8, closer to the actual population mean, standard deviation being 6.98. So I'm going to keep doing that. I'm going to draw another sample, and then another sample, and then another sample. Then let's draw 100 samples. Let's assume that I had 100 students in the class, and each one of them did their own sample. And then let's do another 100. Let's do another 100. And let's do 1,000 now. Let's do 1,000 samples. So what do we see? We see that as we collect samples, more and more samples, even though individual means have a deviation from the actual mean, the distribution of those means again collects around the mean of the population and creates a normal distribution, a bell-shaped curve that is approximately symmetric. And again, as you see, the lowest that we got was a 3, and the highest that we got was an 18, maybe not even 18 yet. We haven't gotten an 18 yet, but these did not appear too many times, maybe just one or twice. So it was very unlikely that we will end up with the lowest possible mean and the highest possible mean. So the concept here is that what do we observe about the distribution of the sample mean? X bar is the notation for the sample mean, that over time, as we do more and more samples, then this becomes bell-shaped and symmetric. The distribution of those means. Did the different distributions of X matter for the shape of the distribution of X bar? So when we had our uniform distribution lately, the last one, did that matter for the distribution of the sample mean? Not really. All of them happened to be bell-shaped and kind of symmetric. So earlier when we did the word length of Sotomayor, this was definitely skewed to the right. And when we drew samples of whatever size, it doesn't matter, size 5 or size 20, we still got a bell-shaped distribution. It didn't follow the distribution of the population. When we did the Amazon star ratings. This was a very weird distribution because 5 and 1 are most popular. Again, when we drew samples, let's go make them a little larger so that we can do go faster. When we did those samples, again, we are getting a bell-shaped distribution. So the distribution of the population of the variable x does not matter. We always end up getting a bell-shaped distribution for the sample mean. The central limit theorem for the sample means says that if we repeatedly draw samples of a given size, for example, repeatedly rolling 10 dice, and calculate their means, those means tend to follow a normal distribution. The sampling distribution of the sample mean, that's what that is called. So we want to know when we collect samples from a population and we calculate the mean of those samples, what should we expect for that value of the sample mean? What do the other sample means look like compared to my sample mean? So the central limit theorem says that as the size of your sample increases, so if you don't stick with samples of size 5, but you increase the sample, maybe make it 20, and ideally make it greater than or equal to 30, the distribution of the sample mean will tend to be a normal distribution. Not just bell-shaped and symmetric, but actually a normal distribution that will follow all the properties of the normal distribution, including the empirical rule. Now, this normal distribution is not as spread as your data, the variable x. It does have the same mean. It has the mean of the x values. So the mean of the means, the sample means, equals the means of the x values, but the standard deviation of your distribution is no longer as big as your original distribution. So here you had a standard deviation of 1.64, but the sampling distribution of the sample mean has a standard deviation that is much smaller. And that is because the means don't go all the way to 1 or all the way to 5. They actually cluster around the actual mean of your distribution, which is 3.4. So that standard deviation, the variance and the standard deviation are smaller. The variance of the sample means is the average of the variance of x if in terms of the sample size. So it is 1 divided by n of the variance of your whole population. And if I take the square roots, the standard deviation of the sample mean is the standard deviation of your variable divided by the square root of n. And because the square root of 5 is a much smaller number than the square root of 20, the larger your size is, the closer you will be to the actual mean. So n is the number of values that are averaged together and not the number of times the experiment is done. So n is the sample size. It is not the size that you repeat your experiment. To put it more formally, if we draw random samples of size n, the distribution of the random variable x bar, which is the mean of the sample, which consists of sample means, is called the sampling distribution of the mean. The sampling distribution of the mean approaches a normal distribution as the sample size n increases. And when n is greater than or equal to 30, it is more normal than it would be if the sample size was less than that. The mean of the sample means, of the distribution of the sample means, is the mean of the variable. The standard deviation of the sample means is the standard deviation of the variable divided by the square root of n, with n being the size of the sample size. I'm going to highlight that here. And also, if you are finding the z-score of your sample mean, the one from the sample you selected, then that z-score will equal to the sample mean you found minus the mean of the distribution of the sample means divided by the standard deviation of the distribution of the sample means, which basically will be the sigma of your variable over the square root of n. So when you have a population for which you know the mean of the population and the standard deviation of the population, then you will know the distribution of the means of samples equal to the size of the sample you selected. The standard deviation of the sample means is called the standard error for the mean, and we will use that very much, quite often, in our inferential statistics that we will be doing in the second half of our statistics class.